We've been talking a lot about the external controls, the hormones, the brain, but there's also internal controls, these autoregulation controls. Now there's two primary methods of autoregulation control. We have the metabolic and the myogenic. Metabolic, chemical-based. Myogenic, muscle-based. So let's start with metabolic controls. Now this might sound kind of familiar to some of the other parts we've talked about, because they're based on similar things, based on oxygen levels, hydrogen ion, potassium levels. So look at these different levels and what's happening. If the oxygen levels are declining, this metabolic control is going to cause vasodilation of the arterioles. Now, one thing to keep in mind, this is looking at blood flow to an area, not necessarily blood pressure, because there might be one area of a muscle that's not getting enough blood flow, or an area of the lungs that don't have enough blood flow. So try to make sure there's adequate blood flow to the individual tissues of every area. So what we're doing here is we vasodilate to open up, to allow more blood to flow into that area. Which, if you vasodilate with no other changes, remember the pressure drops. So this is looking at making sure the tissues get an adequate amount of blood flow so they get enough oxygen and nutrients in the tissues. So this is vasodilation to open up to make sure there's plenty of blood flow into this tissue so it gets an increased amount of oxygen. Helps out to make sure that's balancing its homeostatic levels. So the effects here are the relaxation of the smooth muscle. By relaxing, sure, you're opening up. That's vasodilation. Makes sense. But you're also looking at nitric oxide. NO is nitric oxide. Now, nitric oxide is really going to be the major factor causing vasodilation. So if your system is releasing nitric oxide to a certain area, it's trying to vasodilate those vessels in that area. Now, if you vasoconstrict, that's sympathetic. So that's the flip side. Let's say you've got plenty of oxygen. You don't need that. So high oxygen levels. Vasoconstrict and you reduce the blood flow to that area. Now, that a lot of times is because of sympathetic stimulation or these endothelins. The endothelins are going to be chemicals secreted from the endothelial lining of the vessel. So again, that intrinsic control. Myogenic control, looking at the muscle now. In the case of myogenic control, you're dealing with the vascular smooth muscle. That's going to respond to fluctuations in blood pressure. The whole goal here is to try and reduce the fluctuations. So as your blood pressure changes, these myogenic controls try to change and adapt to match it to keep a constant blood pressure in that area, keep a constant blood flow in that area. So if there is passive stretch, that means the vessel's here, you increase the pressure, it kind of pushes it open. So it wasn't trying to open up. So a passive stretch, that's going to cause an increased tone, which means vasoconstriction. The vessel's going to kind of pull back down, constrict a little bit to make sure it has the same blood flow. You don't necessarily want to just increase blood flow to an area if it doesn't need it. Same on the flip side. Reduced stretch. That means the vessel's used to having a certain amount of push, but it's not there, so it kind of collapses down a little bit. That's going to stimulate vasodilation, because if it's just not pushing enough, that means blood flow is decreased. You want to open it up to try and get more blood flow to that area. So you're trying overall here to keep a constant blood flow to every certain tissue area. Doesn't matter if it's the muscles, if it's into the kidneys, if it's in the lungs. Your body's trying to regulate how much blood is getting to a certain area to make sure that it's meeting the metabolic demands, meeting all of its nutrition, meeting all of its gases, and getting rid of all the waste. So you're constantly monitoring the blood flow to an area to make sure it matches what's needed. So what we're looking at here, I'm going to throw this up full screen. You notice up top, these are vasodilators. So you have these metabolic vasodilators. If you decrease oxygen levels, if you increase carbon dioxide levels, increase hydrogen ion, increase potassium, if you're altering prostaglandins, adenosine, nitric oxide, NO, those all will cause vasodilation of a vessel. But at the same time, you'll vasodilate because of a decrease in sympathetic tone. You'll vasodilate due to atrial natriuretic peptide. But now for the vasoconstriction, if you have myogenic stretch, it vasoconstricts to close down. If you have the endothelins, to cause vasoconstriction again. Or increase in sympathetic tone, or a whole bunch of different hormones. Looking at angiotensin II, antidiuretic hormone, epinephrine, norepinephrine. Those are all causing vasoconstriction. Now the two in green, so this side, those are all intrinsic mechanisms. Things that are more autoregulation for vasoconstriction and vasodilation. But what's in blue is going to be more extrinsic mechanisms. Things that are coming in from the outside to cause an impact, which is what the sympathetic nervous system would be. So looking at these extrinsic mechanisms. Basically, overall, you have to balance the intrinsic and the extrinsic because they both play a role, they both play a part. And if one's saying do one thing, one's saying do something else, it's not going to work out very well. So intrinsic and extrinsic regulation of the vessels to make sure you have adequate blood flow is important. But now there's another long-term regulation here to get into. This thing called angiogenesis. Now, angiogenesis is focusing on tissue requirements for nutrition. Making sure the tissues have adequate oxygen, adequate carbohydrates, adequate amino acids. All the different ions and particles and macronutrients they need have to get the tissues to survive. So if there is not an adequate amount of nutrition reaching a tissue, that's when angiogenesis can kick in. What ends up happening is you increase the number of vessels. So there's already vessels going to an area, but they're just not able to get an adequate nutrient supply. So you add more vessels. The vessels that were there can increase in diameter. The goal, get more blood to that area to increase the actual nutritional amount reaching the tissue. So that's why if a person increases in body size, you need to increase the amount of blood vessels. More body mass means more nutritional demand, more blood vessels to get to that point. So if someone's gaining weight, they need to also match that for this. So that's angiogenesis. A lot of times it'll happen in the heart if there's a blockage of one of the coronary vessels. You'll be having it throughout the body if it's someone of a high altitude area. So high altitude. Well, remember, if someone's at a higher altitude, they have lower oxygen levels in the air. Therefore, the tissues can't get adequate oxygen amounts. Increased blood vessels helps more oxygen get to those tissues. So it's looking at how to modify here. Maybe someone's been exercising a whole lot over the past 6 months and they're gaining muscle mass. Angiogenesis. More blood supply into those muscles. So the blood flow. We've been talking about how you regulate it, but honestly, at rest, myogenic and neural are predominant. So if you're simply just doing normal activities around the house, you're going to work, if you're not physically exerting yourself, not emotionally stressed, so at rest, myogenic and neural control. The neural control is kind of controlling everything, but there's a little fluctuations here and there. The myogenic can vasodilate, vasoconstrict to make sure that's adequate for that particular little area. But during muscular activity, so you're exercising, working out, you're moving around a lot. Now, blood flow is based on metabolic activity. So because your muscles are working more, they'll demand more blood flow to match the metabolic activity they have. And this can override this sympathetic vasoconstriction. Because in case of sympathetic vasoconstriction, closed down, you're decreasing the amount of blood flow. You need to have enough blood flow get into the muscles to adequately provide nutrition to them. So looking at this blood flow chart, you can notice it's going from at rest, moderate or mild exercise, and then full out maximal exercise. Look at the skeletal muscle, 1,200 milliliters per minute at rest. But maximum exertion, that can push 10 times the amount, a huge increase in blood flow. Well, it makes sense because you're trying to match the actual metabolic demand of the muscles. Notice the heart increases. Makes sense because the heart's beating faster. But notice the brain, 750 milliliters per minute. You didn't increase. That's because your brain is still working the same way. You need a constant activity in your brain. Integumentary system, your skin, increased. Well, yeah, you're trying to get rid of heat. So more blood to the skin, evaporative cooling. But look at the kidneys, look at gastrointestinal. You're not really doing a whole lot of kidney utilization. You're not filtering. Your GI tract isn't doing a whole lot of work either. They're decreasing blood flow. Overall, the blood is going where it's needed. That's the key thing. The blood goes where you need it to go. Now, these graphs are meant to kind of just summarize a few things here, kind of try to bring everything together. This first one up top, vessel diameter. It starts with the elastic arteries as some of the largest vessels. But then you'll notice it's going down to the arterioles, the capillaries are going to be the smallest. But then you increase back up venules, veins, vena cava. Well, that makes sense, but then think about this one. Over here, this is looking at total area. Notice right in the middle, those are going to be your capillaries. So they might be the smallest in diameter, but the sheer number of them make them the largest area of all the blood vessels. Now keep that in mind as we go on here to the average blood pressure. Yes, it makes sense blood pressure drops. But notice there's a decent drop right here at the arterioles. Makes sense. And that's kind of a slow decline through the venules, veins, and large veins. And at the end here, this one is velocity. We haven't really mentioned this one yet. So the previous three make sense. We talked about that. But velocity or blood flow. We know you have to slow down for the capillaries. But notice the capillaries are the slowest. Makes sense. Helps out, you're not rupturing, but really efficient transfer, diffusion back and forth of nutrients, metabolic waste. But then notice the speed increases as you go into the veins from smaller to larger. That's because as all those venules converge together into small veins into medium veins converge to large veins. Every time you converge, you're adding the blood flow together to increase velocity. So the fastest flow in the venous system is just before you dump back into the right atrium. So velocity starts off fast in the aorta, drops down, the slowest in the capillaries, great for exchange, then picks back up on the venous system. So even though the venous system, the pressure keeps dropping, velocity will increase. And just a reminder, the entire body is one systemic system. The only thing that's not part of this systemic blood flow is going to be the pulmonary system, the lungs. So remember, there's two circuits, pulmonary and systemic. You're trying to regulate blood flow and blood pressure across all of these at any given moment throughout the day. So a lot of things dealing with blood flow, making sure your tissues have adequate nutrients and also adequate flow to get away and get rid of those metabolic waste products.